So good evening everyone. Let's start with the next topic. So next topic is frequency transformation method. So over here, as the name suggests, frequency transformation. So we will be given with either analog frequency details or the digital frequency details. So based on that, if we are given with the analog frequency details, then we will be transforming the response in a specific way so that we get analog to analog frequency transformation, and then we have to apply either the impulse invariant method or the bilinear transformation method to get into the digital domain. In the second thing, we have digital frequency domain frequency transformation method, where you will be given with the frequencies in the digital domain, and there you have to just apply the transformation. Okay, so in the first case, where we are given with the analog transfer function and we have to apply the analog this frequency transformation method, it is called analog to analog frequency transformation method, or it is also regarded as frequency shifting. Okay, so there are usually four types of transformations. First one is the low pass filter to low pass filter, then low pass filter to band pass filter, low pass filter to high pass filter, and lastly low pass filter to band stop filter. In all these cases, if you see the starting filter, it is nothing but your low pass filter. Why this is so? This is so because it is easier to design the low pass filter. Okay, and then once we have designed the low pass filter, then by applying this frequency transformation method, we can design the other types of the filters. Okay, so if you look into the low pass filter frequency response, it looks something like this, where your minus of omega c is minus of pi by 4 and omega c is your pi by 4. Okay, now what happens is that if we have to convert this into a band pass filter, then if you see, we are having two pass bands, right? Now by applying this transformation, low pass filter to low pass filter transformations, we will be able to segregate these two what you call this pass band fractions. So which are those pass band fractions? These are the two pass band fractions, this one, first one, and the second one. Okay, now when we talk about this low pass filter to low pass filter transformation, so what happens? The width of this pass band fraction, it changes. Okay, then similarly we can go for this high pass filter designing by this frequency transformation method. So what are the different types of analog frequency transformation methods or the formulas? So if you look over here, low pass filter to low pass filter, over here, as we are dealing with in analog domain, so the complex plane would be the S plane. Okay, so S will be replaced with omega p, which is the H frequency of the available filter. Okay, whatever the filter you are having, that filter specification you have to put in, divided by the omega p dash, which is basically the H band frequency of the filter to be designed. Okay, so in the numerator we are having available filter, in the denominator we are having the specification of the to be designed filter. Okay, so this S will be mapped or replaced with omega p divided by omega dash p multiplied by S. Okay, so simple mathematical formula. Second thing is low pass filter to high pass filter. So over here it is S will be transformed to omega p multiplied by omega dash p divided by S. Okay, omega p is the cutoff frequency of the available low pass filter, omega dash p, it is the cutoff frequency of the high pass filter to be designed, right? Now when we get into this band pass filter, if you look into the bandpass filter characteristics, this frequency response, we are having omega L and omega U. So there is one low pass cutoff frequency, one high pass cutoff frequency. Okay. So herein S will be transformed to omega P within bracket S square plus omega L multiplied by omega U. Okay. Divided by S of omega U minus omega L. Are you getting my point? S will be transformed to omega P multiplied by S square plus omega L multiplied by omega U divided by S multiplied by omega U minus omega L. Okay. Then low pass to band stop filter, S will be transformed to omega P S omega U minus omega L divided by S square plus omega U multiplied by omega L. Okay. Over here also you will be having two cutoff frequencies. Okay. Now if you see, these are just simple numericals. Okay. So I am not going into the details of this one. So you will be given with basically HS of any low pass filter, and then you may be asked to design the filter, design the analog filter with the specification which will be provided. Okay. Then we have this digital frequency transformation. So in the digital frequency transformation, that here, as I already told you, we are already in the digital domain. Okay. So herein you will be given with the HZ, and over there you have to apply the transformation. So herein your Z inverse, it will be for the low pass to low pass transformation, Z inverse, it will be replaced with Z inverse minus alpha divided by 1 minus alpha Z inverse. Okay, where alpha is equal to sine of omega P minus omega dash P divided by 2 divided by sine of omega P plus omega dash P divided by 2. Okay. Similarly, for the PF to HPF, we will be having Z inverse will be transformed to Z inverse plus alpha divided by 1 plus alpha Z inverse, where alpha is given by cos of omega P plus omega dash P divided by 2 divided by cos of omega P minus omega dash P divided by 2. Okay. Then we have this LPF to bandpass filter. Z inverse, it will be transformed to Z to the power minus 2 plus of alpha 1 Z to the power minus 1 plus alpha 2 divided by alpha 2 Z to the power minus 2 minus alpha 1 Z to the power minus 1 plus 1. So over here we are having two components, alpha 1 and alpha 2. So alpha 1 is given by 2 alpha k divided by k plus 1, and alpha 2 is given by k minus 1 divided by k plus 1. Here the values of k and alpha, it has been given. Okay. So again, if you see the k and alpha alpha values, they will be having omega u, omega l values. Okay. Then omega p value. Then similarly over here omega u, omega l, omega u, omega l. So everything, if you see, it is basically whatever the frequency component of your low pass filter is there, that should be there, and then you will be having to what filter you have to convert it. The specifications of those filters will be given, and then you just have to put the values, and you will be transforming this Z inverse to the modified transfer function values, Z inverse values. Okay, to get the modified digital filter. Okay. Similarly, we will be having this low pass filter to band stop filter. Over here we have Z inverse, it will be transformed to Z to the power minus 2 minus of alpha 1 Z inverse plus alpha 2 divided by alpha 2 Z to the power minus 2 minus alpha 1 Z to the power minus 1 plus 1. Okay. So alpha 1 it is given by 2 alpha by k1, and alpha 2 it is given by 1 minus k divided by 1 plus k. Alpha over here is given by cos of omega u plus omega l divided by 2 divided by cos of omega u minus omega l divided by 2, and k is given by tan of omega u minus omega l divided by 2 tan of omega p by 2. Okay. Here also the same thing. Now if you look into the first two cases, the order of Z inverse, it is 1, but in the next two cases order is 2. Can you say why? So what? So what does that 2 frequency mean? वो तो कोई भी बता देगा. What does that 2 frequency mean? क्या शांतन जी, विश्वजीत, प्रतीक तो देख ही नहीं रहे. देख ही नहीं रहे हो मेरे तरफ. So why didn't we get it over here? यहाँ पे क्यों नहीं है? नेक्स्ट टू में क्यों है 2?
उसमें जो बैंड स्टॉप है ना, बैंड स्टॉप फिल्टर सिर्फ उसी में इस पर आ रहा है. आपके होता है
किसने बोला? बैंड पास में आ रहा है, बैंड स्टॉप में, दोनों में आ रहा है.
बैंड पास.
He is partially correct. 2 frequencies are, but why that 2 frequencies are coming?
लो पास फिल्टर में लो वाला पास हो गया, हाई वाला रुक गया.
कहाँ पे? इसमें तो 2 अलग अलग है. बैंड स्टॉप में आपका, बैंड पास में आपका हाई पास फिल्टर पास करवा रहा है, वो हाई पास ये हुआ. फिर लो पास वाला जो फिल्टर है उसका तो हाई ओमेगा यू, तो उसका हाई है, दैट इज हाई. सो व्हाट इज द बेसिक रीजन? बेसिकली
रीजन जब हम डिफाइन कर रहे हैं तो लो पास में हम सिर्फ एक फ्रीक्वेंसी से डिफाइन कर दे रहे हैं एक रीजन को, और बैंड पास में हम ऐसे 2 रीजन डिफाइन कर रहे हैं, तो वो दो करते हैं.
हाँ, तो सो व्हाट? दो डिले करने पड़ता. पढ़ाई नहीं करने से ऐसे ही होता है. So basically, I have been telling since the inception when we started this filter designing, this band pass filter and band stop filter, they are a combination of low pass filter and high pass filter. So these are basically the combination of a low pass filter and high pass filter. A low pass filter and high pass filter, if you try to combine it, so for अगर the first one, low pass filter is a first order filter, high pass filter is a first order filter, when you combine this you get a second order filter. It's as simple as that. Okay, so I'm not going into the numericals of this thing because these are pretty simple. You will be getting the values you have to put and just calculate the alpha values and alpha 1 values and just convert it. Now coming to the next method, filter design by approximation of derivatives. So when we talk about derivatives, what is derivative? Derivative is nothing but dy by dx. Okay, for discrete time, how do you find out? You find out x1 minus y1 minus y0 divided by x1 minus x0. Okay, so here also if you see dy by dt, y of nt minus of y of nt minus t, एक इंस्टेंस पहले का, and x1 minus x0, it is nothing but your time period, capital T, right? So this is your dy by dt. So herein what is happening, we are taking the present instance and the previous instance, so it is called backward difference method. Backward difference method. Okay, however there is another difference method where we can use the value y1 minus y of 2 divided by capital T. Okay, but This is the futuristic value if we consider this y1 as the present value. Okay, so this is called forward difference method. Okay, forward difference method for the approximation of the derivatives. However, we have seen that in signal processing we cannot use futuristic values, because in biomedical signal processing we have to deal with the causal signals and systems. When we are having the futuristic system, then that becomes non-causal. So in the approximation of derivatives, okay, filter design by approximation of derivatives, the backward difference method, it is taken into account. Okay, so if you see, we get yn minus y of n minus 1 divided by t, this thing, and as you apply z transform, we get hz equals to 1 minus z inverse divided by t. So for the transformation of the analog system into the digital system, we have to replace s with 1 minus z inverse divided by t. Okay, so herein, if you see the example over here, we have convert an analog bandpass filter to a digital filter. So transfer function has been given, t has been given by backward difference derivative method. Okay, so s, it has been replaced with 1 minus z inverse divided by t, capital T is given, you just solve it and you get the answer. Okay, now coming to the structured realization of the IIR filters. So till now you have been working on the framing of the structures, and what you are doing or working or realizing the filter with the direct form realization method. Okay, now the next method is direct form 2 realization method. So what happens over here, if we consider this system as a subsystem 1 and this next system as subsystem 2, so what we can do is that we can rearrange, because this is what is this? This is basically a multiplicative system, we already discussed, right? So if we are having two systems S1 and S2, and if there is a multiplication, that means they are being cascaded, so one after the other. Okay, so when we are placing one after the other, so if you consider S1 multiplied by S2, it would be again S2 multiplied by S1, commutative effect behavior, right? So if you see, we have just rearranged this in the direct form 2, S2 and S1. Now when we have done this, if you see, these Z inverse terms, they have come near to each other. So these are all delays basically. These are delays. So in direct form 2, what it has been said, that we can combine these two Z inverse terms, and combining 2 we will be getting 1. So instead of 4, we are now having only 2 delays, and by implementing the filter by this direct form 2 method, we have reduced the computational complexity. Okay, then we have parallel form of realization, where you have H1Z, subsystem 1 and subsystem 2, they will be put into the parallel form. Then cascade form, which we already discussed, again over here it can be implemented in this way. So in the parallel form we usually use it for band reject filter, and cascade form we usually use for band pass filter. Okay, now the next is transposed direct form. Okay, so this is bit critical. So herein what we have to do, if you look into the basic architecture from where we start, we are basically starting with direct form to realization. Direct form to realization. Okay. Now, what are the steps to convert this direct form to realization into the transposed direct form realization? So the steps are, first is reverse the direction of the signal flow. Okay, so how the signal was flowing? It is going here, it was going here, then it was going here, it was going here, like this, right? I'm just drawing the arrows, right? Now if you look into this and this architecture, both are same. Okay, just what I have done, I have just put some notes, and this is, I have already told you, this is signal flow graph. Those are contemporary, but for the sake of understanding in a better way, so I have just represented this in this format. Okay, now if you see, these are there. So what is this? This is an adder, this is an adder, this is an adder. Okay, and this is the summing point. You can say this is the summing point, this is a summing point, this is a summing point. Now what is the next step? Next step is the interchange the input and the output. Everything remains the same. We have changed the input and the output. XZ becomes YZ, YZ becomes XZ. Apart from this, what we did? Reverse the rules of the node. If the signal was going in this way, I have drawn it in the opposite way. Okay. So by doing this, what happens? Summing point, it is becoming a branching point now. So here if you see, we are having summation previously. Now if you see, from here signal is coming, but the signals are branching from here. Right? The signals are branching from here. Now by doing this, we have implemented the filter. In the next filter, what we have done? We have just taken this and just reversed it. Because conventionally what we know, that X is on the left hand side, Y is on the right hand side. Okay? Clear? So once you do this, it is your transposed direct form. Now if you have practiced your direct form 1, you should be able to implement this, and if you have not, you will be getting confused, because there are so many things. Direct form 2, over there you have to first draw the direct form 1, then separate it, then join it, right? Then again, if I give you the transposed direct form, then again you have to do so much of things, right? Now coming to the this different types of filters which are being used in the IIR filter. So the most common types of filters, they are basically the integrator. So usually we have the rectangular integration. Okay, so this is the equation of the rectangular integration. So then we have trapezoidal integration method. Okay, you must have done in your numerical analysis classes, right? So trapezoidal integration method, it is there. So the same thing. So what is the advantage in the rectangular integration method? If you see, when you consider this rectangle, there is nearly a triangular area which is getting missed. Okay, so whatever the results you are getting, it is having some error incorporated into the system. Okay, in the trapezoidal method, what we are doing? Rectangular plus a triangular area. But over here also, if you see, there is a dotted line and there is this shaded portion which I am drawing with the red lines, red shade. So that remains unaccounted for. So due to that unaccounted region, the result that you will be getting, it will be having minimal error as compared to the rectangular integrator but still it will be having some error into the integration. Okay, so next, so I am not going into the details, all of you can find it out. I have already told you how to get into this, right? So here if you see, the z has been replaced with e to the j omega t, and then you get this formulas, right? So next is the Simpson's rule of integration, which is basically a polynomial one, which takes into account all of the region. Okay, so this is how you implement the filter. So I can give you implement a polynomial integration, design a filter that employs a polynomial integrator, polynomial function for the integration. So you have to apply the Simpson's rule integration, or I may also ask you design a filter where Simpson's rule of integration will be implemented. Okay, so in that way, so you have to implement all these things, and then you have to implement or realize the filter. Okay, now lastly comes the most easiest part of filter designing. So here we have the design methods for two pole filters. So this is an empirical method for IIR filter designing. Okay, this is the empirical method for IIR filter designing. There is no simplistic method to design an IIR filter than this method. Okay, so what is that? It already assumes that hz is equal to 1 plus a1 z inverse plus a2 z to the power minus 2 divided by 1 minus b1 z inverse plus b2 z to the power minus 2. Done. Pole and zeros equation, you know. Yeah. So here if you see a1, a2, b1, b2s are there. So a1, a2 values, they are already predefined. You don't have to do anything. You have to calculate b1, b2. b1 is equal to 2r cos theta, b2 equals to r square. Theta we already know in radians how we have to calculate, right? So we have to choose the sampling frequency to get the theta. Usually it is given in an example, what is the sampling frequency for a system. Then choose the critical frequency for HPF, LPF, then band pass filter, band reject filter. So HPF, LPF, there is no problem, there will be only one frequency. In the case of BPF and BRF,
omega high plus omega low divided by 2.
so let us take an example over here. Design a two-pole band reject filter with cutoff frequencies at 55 Hz and 65 Hz as per the method given, described here, designing methods for two-pole filters. Okay, so consider Fs as 500 Hz and consider R equals to 0.9. Okay, so theta is equal to 2 pi fc by fs, 2 pi multiplied by 60 by 500, so it is 0.754 radians. A1 2 cos theta 1, 2 cos theta, theta यहाँ से we already got it, it is this thing. A2 1, B1 2r cos theta r square, 2r cos theta r square. Now 0 locations, z equals to minus of a1 plus minus under root of a1 square plus 4 a2 divided by 2, right? Pole locations, b1 plus minus under root of b1 whole square minus 4 b2 divided by 2. Okay, so if you substitute the values, you get the pole and the 0 location. That's it. Okay. Now I will give you some what you call, discuss some aspect where we have, if you see, we have discussed about high pass filter, we have discussed about differentiator, but while implementing, if you see, we are seeing basically a differentiator. If you look into the pole zero plot, it is basically a high pass filter. So what is the difference between a high pass filter and a differentiator? That is an important thing. Okay, now I will tell you the basic thing. If you look into the high pass filter, you're having something like this. So this is the cutoff frequency. Now what happens is that in a high pass filter, the low frequency components, they are being blocked. It is as simple as that. Okay, in a high pass filter, the low frequency components are being blocked. Now when we are having this high pass filter, we are basically having a roll off, where we are having a linear region, okay, and then it goes to a maximally flat region, right? Now if you look into this region, what is happening? At frequencies which is much lower than the cutoff frequency of the high pass filter, there is a blocking of the frequency components, complete blocking of the frequency component. Okay, all the frequency components will be blocked. Then after this, say we come to this point where we are having omega 1. So from this omega 1 to omega 2, if you see, there is a linear relationship. Now in this linear relationship, what it is doing is that mostly the DC frequency and the low frequency components, they have already been eliminated. Now what are the frequency components you are getting over here? Frequency components mean the change in the frequency content within the sample. Okay, the change in the frequency content within the sample, and if that change in the frequency component in this region, if it lies within this omega 1 and omega c, so what will happen? Only those frequencies will be amplified. Only those frequencies will be amplified. So you can generalize the statement that a high pass filter, it acts as a differentiator in the rejection band. Okay, or you can say the roll off of the rejection band. So this, I have already told you, this is the roll off, right? So in the roll off of the rejection band, the high pass filter, it acts as a differentiator. Okay, on the other hand, as we go, if the frequency becomes greater than omega c, then it will act as a high pass filter. That means the frequencies will be passed through the system from omega c onwards. But below the omega c region, in the roll-off region, in the linear roll-off region, we will be seeing that if there are any changes in the signal components, they are getting amplified. Okay, so primary function allows frequencies above certain cutoff frequencies to pass while attenuating lower frequency components. That's true. Amplifies high frequency components and attenuates low frequencies by approximating the derivative of the input signal. Okay, so frequency response passes frequencies above the cutoff frequency with gain gradually increasing as frequency rises. Okay, has a linear increasing gain with frequency, effectively boosting high frequencies. Okay, phase response introduces phase shift that depends on frequency, typically lagging at lower frequencies and approaching zero at higher frequencies. Over here it has a constant 90-degree phase shift. Okay. So ideal response in the frequency domain, sharp transition from stop band to pass band at the cutoff frequency. It linearly increases in gain with frequency. Okay, it linearly increases in gain with frequency. That means it is working in this region. It is talking about this rule of region. Okay, so this is the main thing over here. So you may be given a question, explain why high pass filter it acts as a differentiator, or explain why an integrator is basically a low pass filter. Okay, so this is the explanation. So if you look into the behavior of the high pass filter, so we have this transfer function for the high pass filter, Hs equal to S divided by S plus omega c. It is in the analog domain. Okay, so approximating the differentiation at low frequencies in the rejection band, when omega is much lesser than omega c, the S term in the numerator, it dominates the filter's behavior. Okay, it dominates the S term in the numerator, it dominates the filter behavior. The transfer function, it becomes nearly S by omega c, which resembles the differentiator's transfer function, where the output is proportional to S or j omega. Okay, so that is the important parameter. Okay, this means the filter outputs a signal proportional to the rate of change of input. Okay, as I told you, as there is some rate of change of the signal, it is sensitive to that. It is not allowing any specific frequency component to pass. It is basically in that linear region, the rate of change of frequency is allowed to pass. Okay, so why it acts like a differentiator? A differentiator amplifies the rate of change of input signal in the high pass filter's rejection band, because it is blocking the low frequency near to the close to the DC. It mostly reacts to the changes in the input rather than its steady state value. Okay, thus if the input signal changes slowly, the high pass filter produces a small output, but for rapid changes it produces a large response, just like a differentiator. Okay, so attenuation in the rejection band, in the lower portion of the rejection band, much lower than the omega c, the filtered output becomes heavily attenuated and does not exhibit a differentiated response, because the output is nearly zero regardless of the changes in the input. The thing what I already told you over here, in this region, when it is much smaller, it is completely suppressing the frequency components. Okay, so that is the reason why it is acting as a differentiator in a particular band, in a particular region, in the rule of region, and not in all the rejection band. Okay, so you have to remember that the high pass filter, it acts as a differentiator in the rule of region where the frequency response is a linear response with that of the frequency. Okay, the same thing applies with the low pass filter also. In the low pass filter, what we have, a component like this. So this is the omega c. So here the omega 1 would be somewhere over here at frequencies much greater than omega c. In this region, your frequencies are completely stopped. However, if you are within this region, this omega c to omega 1, there is integration of the system. So if you see omega c by S plus omega c, it is the low pass filter's transfer function, and then by getting this omega is greater than omega c, we get this equation. It transforms into this equation. So omega c by S, which is basically similar to that of the transfer function of an integrator 1 by S. Okay, because omega c, it is basically a constant. okay, for a filter. So with this we complete